Okay, this particular video is over transformations of multiple graphs that are our basic graphs we look at. We'll start with x squared. This is a quadratic graph, or f of x equals x squared. This is before any transformations of any sort like this have been applied. And your base graph is you go down and you hit here, you hit at the point 0, 0. So let's go ahead and apply a point there. You always go through the point 0, 0, then the graph goes up through the point 1, 1. And then as x goes to 2, y goes all the way up to 4 because this is a squaring function. 1 squared is 1, 2 squared is 4. And if it was showing up, 3 would end up being going all the way up to 9. Okay? So you need to know the parent graph for x squared. When you see x squared, you should know it looks just like this. It goes to the point 0, 0. Over here it goes through 1, 1. Over here it goes through negative 1, 1. When you move out to 2, you end up squaring that going up to 4. When you move out to positive 2, you square that, go up to 4 as well. Okay, square root of x looks like this. Now the square root graph, again, it starts at 0, 0. Just all of these go through the origin. Now this one is only, I guess you could think of it as half a graph, because it doesn't go through the whole entire graph. And then you're going to go ahead, your next point is again 1, 1, because 1 squared is 1. But then when you go to 2, you see the square root of 2 is 1.4 something. So you have to go all the way to 4 before you end up back on a whole number or an integer value, because the square root of 4, when x is 4, the square root is going to be 2. And this is the inverse of the squaring graph. You'll remember that when x was 2 on the squaring graph, y was 4. Well, now when x is 4, y is 2. So they're the inverses. Absolute value graph looks like this. Absolute value graph, again, these are all parent functions, starts at the point 0, 0. And then when x is 1, y is 1. When x is 2, y is 2. This is a linear graph of a slope of 1 on this side. As x goes up 1, y does 2. On this side, it's got a negative slope. As x goes up 1, in this case you're moving from a negative 2 to a positive 2, you go down 1. So this has got a negative slope of 1, and this has got a positive slope of 1, and both of them meet at the point 0, 0. So your absolute value graph is basically composed of two linear graphs, with slope 1 as the parent function. The next one we talked about was x. This is just your linear graph, x equals y, or y equals x. All right, so this is, again, this has a slope of positive 1 from start to finish. So as x goes to 1, y goes to 1, x is 2, y is 2. X is a negative 2, y is a negative 2. X cubed is the other one. Start with the point here at 0, 0 as usual. The 1 cubed is 1. Then when you go up to 2, you have to go all the way up here to, okay, whoops, this point's going off. But what I'm trying to do is get right here at 8. Okay, when x is 2, again, this is a cubing graph. 2 cubed is 8. I can't get this point up to 8 without it shooting off the graph, but you should get the idea. All right, so the points that are important here are 0, 0, 1, 1, and then 2, 8. And then 0, 0, negative 1, 1. Again, when you cube negative 1, it just becomes a negative 1. And then, of course, it goes at a negative 2. It goes all the way down to a negative 8. So that's the parent graph for x cubed. And that's all I'm going to look at. That I'm not sure what that other thing is. Okay, so let's go back to x squared and start talking about our transformations. Okay, so right now, d, which is my y value shift, is at 0. So we're not shifting up at all. Okay, so let's go ahead and shift up to 3. I'll get as close to 3 as I can. That's about the closest I can get, is 2.97. You'll notice when you add d to the function, this is the squaring function, it pushes it up 3. What that looks like, as far as, that's what it looks like. But we've got here is we've got f of x was equal to x squared. Let's go ahead and look. It was originally the parent function. And then we shifted it up 3, and it went as plus 3. All right, so that's what it looks like as the squaring function. Okay? Now, going back to the picture, let's say I change this to the square root of x. It's going to have the same impact. We had a point here, adding 3, or something really close to 3, goes from 0, and then you go 1, 2, 3. So this basic starting point at 0, 0 is now at 0, 3. This point, which is at 1, 1, is now at 1, 4. It's shifted up 3. This point that was at 4, 2 has now shifted up 3 to 4, 5. Wait, yeah, that's right. Okay, so that has the function, and what that would look like And here we have what the square root function would look like. F of x equals the square root of x, which was your original graph, plus 3 when it shifted up. Let's go to the next one. Absolute value of x, it's going to look exactly the same, only now, once again, all the points on the original absolute value parent function, which are red, everything has shifted up 3. And if I were to write this, I would just simply write f of x f of x equals the absolute value of x plus 3. Okay, so I'm doing a few of these just to show you that the actual shift looks the same. The only thing that changes is the type of function that's being shifted. So you don't want to make this harder than it is. Okay, let's go to another one. I'm going to put this back at 0. If I can get it back there really close to 0. Oh, there it was. Almost got it. Okay, there's at 0. Let's go ahead. We'll stay with the absolute value on this point right here. Let's go ahead and see what c. Now notice c is inside the function itself. For instance, c would, in the absolute value graph that we have, would look like this. It would be the absolute value of x plus, let's just do a shift of 2. All right, so the actual shift for this one is going to be inside the absolute value function. I want you to compare these two. This was outside, adding 3 after you had written your absolute value function. Now it's inside. So when we move this to 2, which I just said, you can see that this is really hard to control here, but okay, well that's close enough, 2.2. It's a little bit bigger, but there's no way to really make it do what I want it to. Anyway, you can see, now one thing I want you to see, this shifted in a positive 2 direction, and the way I wrote it was as a plus 2, but you'll notice that the shift was actually left. And that's what happens when you have a shift. Your shift on your x-axis goes in the opposite direction of the sign, because the shift is actually f of x is x minus. If you look up here, well, it says x plus c, but it's actually supposed to be x minus c. So you're shifting in the negative, well, you're shifting in the opposite direction as the number, so 2. So now if I go to a negative 2, whoops, I went too far, I'm going to end up with, it's shifted over here to the right. And what I get here is x minus 2. So when it shifts to the right, when it shifts to the left, it is actually going to be positive, and when it shifts to the right, it's going to be negative inside of there. We're going to go ahead and do the next transformation with a x squared. Let's go ahead and look at this one because this is a little bit easier to explain. This has these are both multiples. Here's where you're multiplying your x, and here's where you're taking a multiple of your y. And the easy way to think about this is rise over run. So here you're doubling your rise, right? Or you're changing your rise. So right now it's 1 times. Let's move it up to 2. This is hard to stop. Okay, let's go ahead and put a point on here. Let's go ahead and move this here. Okay, so before our point was at 2, we went, the red graph is the original one. You went over 1, and here, let me go down here. Over 1 and up 1. Remember, we had a point at 1, 1. Now we're going over 1 and up 2. So our rate of change for our y value is actually doubling. If we go to this point where we went over 2, we went over 2 and up 4. Now when we go over 2, we're going to actually double that original value, which was at 4, and now it's going to go over 2 and all the way up to 8. And you can see the same thing happens over here. On the original graph, when I went over 1 in the negative direction, I squared that and got 2. I'm sorry, when I went over 1, I squared that and got 1. Now, because my y is being doubled when I'm going over 1, instead of being at 1, my new graph is at 2. And I'll go ahead and move this out to 3 just so you can see what happens. It's going to triple all these values. Let me get as close to 3. Okay, that's about as close as I'm going to get. Now, when you go over 1, instead of going up 1, you're actually going to go up 3. Same thing here. Let's see if we can have another one. Over here it's the same thing. Here my y value for the original graph was at 2, now it's at 6. Let's see, when you go here, it goes off the chart. That's what I was afraid of. So you can only see it, you can only choose a y value from the original graph that you can still see 3 times as much on your new graph. But basically what you're doing is you're taking your y values and you're tripling them here because my coefficient is 3. Now going back to 2, I'll show you what that looks like as an actual equation. Let's go ahead and look at it. So what we have here is 2 times y is going to give us x squared, or we can rewrite that as f of x equals 2x squared. I put parentheses on this, they're not necessary, just to show you that the 2 is not acting on the squaring function. It's acting on the entire function. It's not in with the x. So this is what it looks like because the parentheses aren't necessary. So this is completely different from f of x equals 2x squared, where the 2 is acting on the x. So I want you to notice the difference here. Here the 2 is not acting on the x, it's acting on the function x squared. So it's actually attached to the y. It's just that it's not written that way. In this case, the 2 is actually directly affecting the x, so it will have a different look. And what that will look like, when your stretching factor is on the x value and not the y, what happens is it actually does the opposite of what you would think it would do. Now you would think you're doubling your x's, but you're actually not. You're not doubling your x values. What you're doing is you're changing your slope. Remember the denominator? You have to remember the rise over run. Your x is in the denominator, so you're making your change in x bigger, which is making this entire fraction smaller. So the graph is actually rising more quickly than it's running. Okay, so once again, here we have the value on the x. I put a 2 there, which matches up with this right here. F of x equals 2x quantity squared. So now the 2 is acting on the x. And what you end up with is you end up with a really narrow graph. So as the value acting on the x gets bigger and bigger, the graph still gets narrower and narrower, narrower and narrower. All right, so it's important to understand that it kind of has a reverse effect. Putting a 2 on the x has almost the exact same impact as putting a 2 on the y. And this makes sense if you think about it. Here, if you just had just x squared, let's look at this one real quick. Let's say you just had f of x equals x squared. If that's what you ended up with, then you're going to, let me go ahead and get rid of this. So this is x squared. So let's think about the point. And if you ever wondered, just ask yourself, well, let's say, what if x was 2, what would y be? Well, if you plug it into this function and 2 and you square it, y is 4. That's pretty straightforward. So then the next question is, what will happen if I plug in a 2 into this function? So if I take 2, I'm going to get 4. 2 times 2 is 4, and then when I square that, I'm going to get 16. So you can see that the y values get large really fast because you're squaring a much bigger number. You're squaring something in here beside just the x. You're squaring the x and a multiple of x. So that makes sense why it would get bigger and bigger. So these two have the same effect. Adding the 2 to the x or the 2 to the y actually has the same impact of stretching it. Okay? Going back to this, so that's what you get when you double that. Let's go ahead and look at a cubic. We haven't looked at a cubic. So there's your original graph. Once again, there's your original function, sort of. I'm trying to put it at 1. And then as you increase it, the graph gets narrower and narrower because the thing that's being cubed is you're now multiplying your x by 3, and that's being cubed, which is making it grow really fast. Now if you go below 1, like this is about a negative 1/2, now you're taking the x value, you're multiplying it by something much smaller. So when you think about it, you're taking whatever extra, let's plug 2 in there. You're taking 2 and then you're halving it. So now instead of cubing a 2, you're cubing half of 2, which is a 1. So this is going to grow slower because your y value is dependent on a much smaller number being cubed. And that's why this, as you get bigger and bigger values, you're actually changing your run, and so it's getting fatter and fatter and growing more slowly because your run is changing, which is on the bottom of your fraction, so that means your actual slope is getting smaller and smaller. Once again, your run's on the bottom, so when you change your values, you have to remember that you're actually changing the rate of change between your x and your y. Okay? Now let's go ahead and reset this, and I'll go ahead and choose, what haven't I used? I'll go back to the square root graph. Let's go ahead and see what happens when you add a reflection. Now what I just did is I added the reflection of the square root graph on the function itself, not on the x. And it flips across the x, because what you're doing is you're making this is a negative f of x. Another way of thinking that is a negative y. So here your y value is positive. We'll go ahead and add a point. You have a positive, what is that, a positive 2. And by putting a negative on it, you make a negative 2. So if you need to think about, I've got a positive y, negative y, okay, that's flipping across the x. So the actual reflection is across the opposite axis that you might think. Notation-wise, that would look like this. F of x equals a negative on the x squared. Now the obvious counter, oops, I didn't mean to do that. The obvious counter argument or the counter example of this would be asking to find what happens when the negative is on the x itself, or in other words, inside the function with the x. And the answer is, we will see. So now I have the negative actually acting on the x. Here it was acting on the function, which is the same. Basically what you're looking at, this is the same as looking at something like this. What might make more sense of this is the same as putting the negative on the y. Okay, because think about it. If you divide by a negative, this becomes negative, this becomes positive. So the negative is not inside that square root. It's on the y value itself, and that's why it's changing the y values. Adding the negative to the x, okay, is going to have the impact of changing the x. The x itself is being made negative, so it goes from a positive 4 all the way to a negative 4. So once again, that makes a difference as far as how you see it. Okay? You can do more than one transformation if you did the negative and the positive. So the negative would have the impact of shifting it. Well, they did it in this direction. They went ahead and did this first and then this, which is fine. So it has the impact of reflecting it across the x and then reflecting it across the y as well. One of the things you need to realize is remember the negative on the quadratic, you can see, and this is a negative, this is what we've been working with. This is a negative function, which means it's going to open down. We've been actually doing the leading coefficient on a quadratic is negative, it opens down. However, if it reflects across if you make the negative on the x, which means your x was 4 here, your x was 2, it went to a negative 2, you can't tell. Because a quadratic is a symmetric graph, it's actually an even graph. You guys learned about even and odd functions in geometry. This is an even function, and when something's symmetric with respect to the y-axis, reflecting it, that's what you did in geometry. You talked about reflecting. You can't tell there's a difference. There's no difference in the reflection, so you can't really see that had happened. But you can see when you reflect across the y-axis. In other words, you change the value on the y from a positive, what's this, a positive 4 down to a negative 4. That does show up. Okay, I think if I do it like this, it does, yeah, it just does that, which you can't really tell. Okay, now let's do a couple of transformations. Let's say I moved this over 1. We'll go ahead and increase the shift by 1, and I'm going to put a negative on this. Now this ends up being a little different, and this is the one you have to be careful of. When you're shifting inside the x and you're reflecting, it's going to do the opposite of what you think, because this is a positive one, so you would shift left 1. But if you do that first and then you reflect, you should be over here. So what you want to do to be careful not to confuse yourself is you need to think of it in this sense. I'm going to go ahead and draw on this to kind of make it a little clearer, because it's harder to shift that. So we have a negative x plus 1. Well, if you just look at it as is, you'd think, okay, I need to shift over 1. So my new graph is going to be over here, and it's going to be shifted 1. That's not a perfect picture, but you can see the vertex has scooted over here. And then the negative on the x would make you think, okay, I need to go from a negative to a positive x. So I'm going to shift, I was here, I'm going to jump all the way over here, and now my graph is going to look like this. It's going to go through, so my final graph should be over here. But what you'll see when you look at this is that's not actually where your final graph ends up. It ends up on the left. So once again, you have to kind of rethink this, what you're going to end up with. So now, when I draw the graph, I'm going to draw it over here. So it goes through the x-axis. This is freehand, so I'm not doing a real good job. But anyway, it goes through the x-axis. It's supposed to go right here. We'll pretend like the vertex is right there. Okay? And then the negative, think of order of operation. I'm going to do the negative inside the parentheses first. So that means shift right 1. So I'm going to go up here and get a pen color of red, and I'll shift right 1 with my red. So I start over here. I've shifted right 1. And then I'm going to go and shift, then now I've done the right one. So the red was the x minus 1. And then I'm going to go ahead and choose the minus sign here, which is going to flip me across the x-axis and land me over here. That's not a very good drawing, but you get the idea. So if you factor the negative out and you do what's inside the parentheses, your graph will actually look like it's supposed to. Notice my final graph is over here, which is exactly where it's supposed to be. When you have something like that, you need to remember to factor that negative out. Okay, now let's talk about just some more generic shifts and multiple shifts, all right? Now you'll notice this says, whoops, this should be g of x. We're saying now that f of x, which is our function, is equal to whatever g of x was before, which g of x could have been a squaring function, it could have been a cubic function, it could have been the square root function, it could have been the absolute value function. I'm not sure what g of x was. I just know g of x was a function that was a parent graph to begin with. And now, first thing you want to do in this case is list all of your transformations. Well, what's happened to g of x? The easiest way to do this is usually, again, order of operation. Let's do what's in the parentheses first. Well, what happened to g of x in here? What did that do to g of x? Well, that is x minus 3, so that shifted on the x-axis. I'm going to write this out all the way. Right 3, because remember you shift against the sign when you're on the x-axis. Then go outside of your parentheses. I would do the up or down shift last. It doesn't matter, but it's usually safer because you don't make mistakes that way. Look out here. This is it stretched it by a -2. The y values, because that 2 is on the y. It's not on the x, by a factor of 2. So now the graph is twice, the y values are twice as big as they were, so the graph is stretching and going up quickly. And then this negative here, again, this negative is on the y, so you reflected across the x-axis, because if you're changing your y values, you are actually going from positive y's across the x-axis down to negative y's. And then finally, this is a shift down 4 units. All right? So that's what's happened. So let's go ahead and do this on the actual which one did we'll just do it on the square root graph. Okay, so let's see. We went what was this up 4? Oh, down 4. Okay, so let's go ahead and go down 4 if it'll go down 4. Yeah, there it goes. Okay, that's about 4. And let me go ahead and add a dot. Okay, so that's good. You can see it went down 4. Let's go ahead and put it on something that actually has a specific value. And then inside here, what did we do? I forgot already. We did a -3. So I'm going to go to a -3. Okay, so now we've scooted over in the positive. Remember, now we went down and we've scooted over in the direction of, I'm going to go ahead and just move this center one. Okay, so we went down 4 and then we shifted over right. Remember, you go against your sign. If it's negative, you're going to the right. So -3, and then we we already reflected across the y, and we multiplied the y values, not the x, by 2. So let's go back here. Here's your y value being multiplied by 2. So that made it skinnier. See how it goes from not very skinny to really tall? It moves faster. It's making it much more steep. And then the last thing we did is I think that negative was on, let's look one more time. The negative was on the 2. It wasn't on the x, it was on the y. So we're going to go ahead and put a negative on the value, and that flipped it down. So your final graph would end up down here. Okay? And this is supposed to be, hold on. The only reason that's a little weird is because I wasn't able to make this exactly 2. But it should be right here at this point. This one is a little bit off of 3, and this one is just a little bit off of 2. But that's basically where it would be right there. That's what happens when you do those shifts. So that's how you would do multiple shifts. And the most important part is to know what each of these mean. Shift left on the X means you're going to go negative inside here, a negative A. Stretch the Y values by a factor of 2. That's when you multiply something in front here. That could be a 2, 1, whatever. Reflected across the X-axis comes from the negative. If that negative is gone, then this is no longer valid. You're just stretching by a factor of 2. So that's not a negative 2. That's a negative and a 2. Okay? Now, just for what if this were 1/2? How would that impact my graph? What would happen? Well, let's look. So this is 1/2, 0.5. So you can see it makes it a lot flatter. And that is when I add the 1/2 in front of the Y. Remember, we're not adding it to the X. Adding it to the X has a completely different impact. Okay, so let's do another one just to practice with the X-axis. We're going to let this be negative, and this is going to be +2, so I need to change that. This is going to be, let's make this a plus, just do a +1, something simple to draw. And we're going to go ahead and talk about what the transformations are. Inside the parentheses, once you see that negative on your X, it's strongly recommended, not required, but strongly recommended that you go ahead and rewrite it. Save some room so we can see it all. So let's go ahead and factor the negative out, which makes that a positive X, and that becomes a -2. So when I write my transformations, when I list them, I'm going to do order of operation, and they'll actually be in the correct order, which is what I'm looking for, okay? So inside the parentheses, we have X minus 2, which means we're going to go right 2, okay? And then right outside the parentheses after the -2, we have the negative, which means we're going to reflect. A negative means we're going to reflect. The question is reflect about what? You are going to reflect about the Y-axis. And again, it's kind of in the opposite. If it's negatives on the X, you actually reflect across the Y. If the negative's on the Y, you reflect across the X. Let's go ahead and do this with a cubing function. Minus inside the X, and then a +2. Okay, that's as close as I'm going to get. And then +1 was added on as the Y. Okay, so let's go ahead and add a point to this. Let's go ahead and scoot this down. We were originally at the point 1, 1. Remember, a cubic goes 1 cubed is 1. So you can see the transformations. Order of operation, you would have gone right 2, then reflected about the Y-axis and gone up 1. I'm just curious to see if it's obvious if we do that in the order. So you went right 2. Let's see what happens. It's going to the left, which is what it should have been doing. Which actually, what happened is you went right 2 and you didn't reflect across the Y. You reflected across this line right here. Let me show you the difference. Watch what happens. Right at 2, there is an axis of symmetry. And so you're reflecting across that. That's why this particular graph is so confusing, is you're not actually reflecting across the Y. You're reflecting across the line at X equals a -2. So that's why it's not ending up over here, and that's why the order of operation is important. So we reflected across at 2, and then the last thing to do was go up 1. And so you can see the whole graph shifts up 1. Okay? And there's your final graph. Be sure that you understand the order that you have to do your operations in, and make sure that you recognize what those are, what those different transformations are, and write them in the correct order, which usually is going with order of operation is the best way to do it. But otherwise, just remember what they are specifically, because if you get one thing wrong, you'll get most of your credit. But you want to have an understanding of what direction, what goes where, and what order it should actually occur in.